Yes, your day. Number 8. Okay, we can look at number 8. How about you get number 8 out? Your day. Get your stuff up. So here today, you want to do number 8. 8 says, what is the tension in the rope that joins the two blocks that are pulled by a constant force of 500 newtons in the diagram below? Okay. Free body diagram is going to look like, here we go. Let's just do this. Free body diagram looks like this. Let's clean it up. So I've got FGs for both blocks. I've got FNs for both blocks. Both blocks are experiencing friction. Force of friction is mu times Fn. Neither of the blocks are on wheels, so they both experience the friction. And then I've got Ft back on this block, Ft forwards on this block, and 500 to the right on the the block I labeled block 1, or the right-hand block. So that's what your free body diagram should look like. When you make your F net equals MA for the system, this is what the equation is going to look like. Starting, like if we call, which I did, to the right positive, it's going to be this guy positive minus these two plus this one minus that one. The expression looks like this. FA minus FT minus the friction on block 1 plus FT, because it's the same FT, minus the friction on block 2 equals the combined mass times the acceleration. So I plugged in all my values, I made my cancellations, and I got this. 500 minus the 2 friction forces equals 30 times A. A is 15.5 meters per second squared. It's still a massive acceleration. Then I went and I solved this thing for that tension force. If you use block 2, tension minus the force of friction, you get 155. If you use block 1, nope, you get 166.76. Never mind, that's what you get. This is what you get when you plug the values in. So the tension between the two is 167 newtons. Isolating block 2. Which is that guy there. Does that make sense? The free body diagram is the most important part. You got everything labeled, you'll be fine. Is there anything else anyone would like me to do from the stuff I assigned? 3, 4, 3, 4, and 8. Yeah, did you get your questions answered? Because you had some questions at lunch. I can't remember if I answered all of them. Okay. For 3 and 4, if the thing's moving at constant velocity, that means there's no acceleration. So in 3, tension up equals gravity downwards. And then in question 4, they give you an acceleration, and it's accelerating upwards. So it's going to be Ft minus Fg equals Ma. If you didn't play with question 3 and 4, they can actually make an attempt to do them. You should. There's some interesting stuff that happens in there that if you haven't looked at before I give you a quiz or a chapter test, will certainly mess you up. So do take the time to at least do the questions I assigned. I'll be assigning all of the rest of them today. So if there are no other questions, let's go back and look at pulleys. Find me this page. I don't know why this isn't working. 1 second. Let's remove you. Yeah, remove you. We're going to add that thing. Yeah. Except it's going to be that guy. Aha! There we go. There. The webcam portion's been not working all day. Okay, here we go. So, you stay on that page. I'm just going to flip back to this page for a second. Friday, I introduced you to the concept of tension. We looked at how ropes connecting two objects are analyzed and behave how tension is the same throughout, and depending on which way you're looking, or which object you're looking at, which way you're looking at it, tension is the same throughout a rope, but it might act two different ways. At this end of the rope, it's acting to the right. At this end of the rope, it's acting to the left. At every point in between, it's acting both directions equally. We treated the objects as one system to find out how they accelerate together, based on some of the arguments I made. And then we looked at isolating either one to find out what tension was. I introduced to you friction. Today, we're going to look at what happens if you bring in some pulleys. Now, the point of a pulley you good? Okay. The point of a pulley is just to change the direction of a force. So I'm considering two equal masses hanging from a pulley. There it is. If we, again, ignore the mass of the rope, and friction in the pulley, we assume the rope is massless and the pulley is perfectly lubricated. What forces are acting on these two masses? Gravity. Each one has gravity acting which way? Downwards. So Fg pulls down there, Fg pulls down here. What else is acting on these two masses? Tension. Which way? Upwards, on both of them. So that one's got its force upwards, this one's got a force upwards, this one is tension, this one is tension. And in this case, given this example, what can you tell me about these two tensions? They're equal, they have to be equal. Because it's the same rope that goes up, over, and down. Now, the one I'm going to show you here is a method some of you might like, some of you might find this easier, some of you might find this more difficult. A way to solve problems that involve pulleys is to unfold the system. Once you've drawn the free body diagrams on the pulleys as they are, sometimes it makes sense. Some students like this, some students don't. I don't personally care for it, but it's a method that I'll show you that some students quite like, is to take the blocks, pick them up off the pulley, stretch them out, and lay them down flat. Because that's all the pulley's doing. It is just changing the direction of what would have been a flat system. So I'll have a block this way, the rope between them, a block this way. Each one of these is labeled M. It's important to do the free body diagram on the pulleyed one first, because when we pick it up and lay it down flat, the directions on all these forces are going to change. These two FGs, instead of acting down, are going to act which way on this diagram? If I take these out, lay them flat, this guy acting down is going to act which way in this diagram? Let's go to the left. This guy is this guy. Picking him up, rotating him, laying him flat. Tension's acting that way. Gravity was opposite tension, so gravity's got to be going this way. I'm not, so Liam, the confusion sometimes comes when I'm not actually taking them off the pulley and laying them flat. I am, having done the free body diagram, we're going to analyze it as if we were, and gravity behaves, like, so if gravity was pulling down here, it's pulling to the left over here. If it was pulling down here, it's going to be pulling to the right over here. Because the upwards that was tension is now to the left on this guy. Now, some students find this easier to analyze. We still need a direction to choose to be positive. This one, when we laid them out flat like this on Friday, we would say left is positive or right's positive. We'd ignore up and down. If I call to the right positive here in this diagram, what does that do to the pulley? If I take this thing, pick it back over, drape it back on the pulley to line up these forces and these tensions, what does to the right in this diagram actually mean here? Down is positive because, well, which down is positive? Because this is the same direction as this guy, but it's the opposite direction of this guy. And both of these point down. So if to the right is positive in this diagram, what that means is this gravity force, which is this gravity force, is positive, and this gravity force is negative. So when you're dealing with pulleys, you can't just say up and down anymore. You have to pick a spinning direction for the pulley. To the right here means up, over, and down this way is going to be positive. So anything that acts opposite that is going to be negative. Pulleys do more than just change the direction of the forces. They actually change the direction that we can call positive. You can't just say up and down anymore. Because the pulleys change the direction of that too when we analyze these kinds of things. So in this case, up, over, and down to the right, or clockwise, is effectively what we're determining as positive. Now, clockwise is a dangerous word to use because I have so many students who can't actually tell time. They don't know what clockwise means. Yeah, your eyes get really big. You think that, yeah, I'm totally serious. If I told my grade 9s clockwise, probably half of them, at least, would not know what that meant because they can't tell time on a clock that looks like that. And normal, quote unquote, digital clocks don't have a clockwise. They just go. Yeah. So in this case, I'm hoping you all understand what I mean by clockwise. So up, over, and down to the right is what we're going to call positive. Now, you don't have to analyze things this way. If you're content to use the pulley, you can certainly leave it that way. I'll show you what it looks like when we've got some numbers here, and then we'll play with it in some other circumstances. Let's take a look here. I've got two masses hanging from a frictionless pulley. At rest, they are released. What's going to happen here? What forces are acting on these two blocks? Gravity is acting on both of them. So this guy's going to have Fg down. This guy's going to have Fg down. And let's go actually plug in some values here. Fg was found by multiplying the mass times 9.81. So that's this. The mass of this block is 6. Actually, I'm just going to use 9.8 because that's what I did last time. 6 times 9.8 is equal to 58.8 newtons. And this guy is going to be 4 times 9.8. Fg for that guy is 39.2 newtons. So what's going to happen to that system of blocks? Yeah. What do you mean to the left? Yeah, the 6 is going to fall down, and the 4 is going to rise. Yeah. So if we were to analyze it this way, we take these guys, we pop them off, we place them down, we rewrite these. There's my 6 attached via rope to the 4. This Fg is now acting to the left. This Fg is acting to the right. Because here today this block is dropping and this block is rising, which way do you want to call positive? In this diagram, you want to call to the left positive. Okay, that makes a lot of sense. So in this diagram, if this is the one you're analyzing, what would be considered positive? Counterclockwise. Up, over, and down this way would be considered positive. Now, the only forces we haven't labeled yet on this thing are tension. So on this diagram, the blue one here, tensions are going to be acting towards each other. And on this diagram, the tensions are also going to be acting towards each other. one up over the pulley clockwise and one up over the pulley counterclockwise. And to find the acceleration of the system, we approach it the exact same way we did yesterday, or Friday. If I'm going to call this, and it also doesn't matter which way you choose to set it up. You don't have to redraw it like this. You can leave it like this. You just need to be careful with what you're calling positive. But everything here starts with F net equals MA. If I call to the left, we call to the left positive in this blue diagram. Start at the left, work your way to the right. This guy's going to be positive, is 58.8. That's negative. That's positive, and they're the same, so I can call them the same thing. Minus this 39.2 is going to equal your combined mass of the system, which is 10, times A. This is the same. If we're calling clockwise or counterclockwise positive, this guy's going to be positive, that guy's going to be negative, this guy's going to be positive, and this guy's going to be negative. The procedure is the same, whether you pull it off the pulley or not. And then at this stage, it's the same as the stuff we did on Friday. Because these tensions are the same, they're going to cancel. And we're going to be left with 58.8 minus 39.2 equals 10A. You solve that thing. I'll tell you what the value is for that acceleration. We're going to get 1.96 meters per second squared. So I'm hoping that you're seeing it's a small jump from the stuff that we did Friday. The pulleys just changed the direction of what's going on here. In this case, FG is acting, I guess, towards the Earth. But in one case, it's positive. In the other, it's negative. You got to make sure you don't call them both the same thing. Otherwise, you're going to get results that don't make sense. But finding the tension is exactly the same thing. To find the tension in the string, we now have to isolate a block. Which block do you want to isolate? The 6. The 6 makes sense. I mean, you can make an argument for 4 making sense. You want to do the 6? Let's do the 6. In the 6 kilogram block, F net equals MA is going to look like what? Yep. Yep. You bet. So that isolating for tension means I'm going to add this guy over and I'm going to subtract this thing over. So FT is going to equal 58.8 minus 6 times 1.96. I did not leave myself enough room to write that. So then FT is going to equal 58.8 minus this. The value I got for that is 47.04. So that's the force of tension acting all the way along this rope in both directions. The procedure is the same. The pulley just adds a bit of a snag. So again, like Friday, when solving for acceleration of the entire system or the whole system, we consider total mass, just like we did on Friday. When finding T, we only use one of the objects. Now, again, it doesn't matter to me which of these methods you use. If you want to redraw it like this, or if you want to use the free body diagrams like this, whatever you're comfortable with, do that. Personally, I don't love having to redraw, but that's just a personal preference. I'll show you the technique because I do know a bunch of students I've taught have found it useful. Okay, we're going to do a couple more examples that I will free you to play. Okay, we have this setup. We have an 8 kilogram mass hanging or sitting on a table and a 6 kilogram mass hanging off the table. Now, in the real world, if I were to set this up in class, what would you expect to happen? Here it is. You're going to say that this is going to keep dangling? Okay, yeah, so like it won't move is what I'm hearing you say. Is that what you mean? Say it again. It will not be displaced. Okay? What's keeping it there? So the tension in the tension in the rope is what's going to try to pull the 8 kilogram block towards the edge of the table. So the only thing holding the 8 kilogram block there is, you said it, friction. So in the first example, I'm going to do this question twice. I don't know if you've noticed yet, but this one and the one below it are exactly the same style. Like the numbers, the picture are identical. The only difference is in the first one, the mass is on a frictionless table. I went out at lunchtime, I got a bunch of Vaseline, and I greased up the table. And then I set this thing up. If, as you say, friction is the only thing holding it there, and I've greased the table, what's going to happen to the system? It's going to fall. The 6 kilogram is going to drag the 8 kilogram block to the edge of the table. Does it matter what the mass of this thing is? No. I could put 1,000 kilogram mass on here. I could put my car somehow, balance it on the table. If I've greased this thing up and friction is truly zero, it doesn't matter what this mass is, it will drag it to the edge of the table. Because friction is the only thing holding it here, which is wildly counterintuitive for a ton of people. So let's analyze this as if this was a frictionless system. The pulley is always frictionless. I'm going to stop saying this eventually. This is always assumed. Assume always that the pulley is frictionless. The rope has no mass, the pulley is frictionless. But this is not new. The table is frictionless. That's weird. We can't always assume this. So let's play with it as it is. If this thing is frictionless, let's draw a free body diagram. If it's frictionless, the only forces acting on the 8 kilogram block are what? Tension which way? Tension to the right. What other forces are acting? Gravity down this way. What else is acting on this guy? Normal force which way? Why is there a normal force acting on that block? Because it's sitting on a surface. Sweet. Are there any other forces acting on this? Do I need to find values for Fg and Fn? Why not, Granada? They're equal and they're opposite, and there's one other reason. There's one other reason. The only reason to calculate Fg would be to calculate Fn, Lena. The net forces, we only consider the net force in the direction of motion, and tension is the only thing that's acting here. Because there's no friction acting to the back, the only reason we would find Fg is to give us Fn, and the only reason we'd want Fn is if we needed friction. We don't in this example, in this version of the problem. These are equal and opposite. They cancel each other out. They have no bearing on the acceleration, and there's no friction. So what's the free body diagram for this guy? Gravity down. Do I need to calculate this one? Yeah. Why? Yeah, because this force of gravity right here is the only reason this system's going to move. So this we need to calculate. That's going to be 6 times 9.8. It's the same value we had before, 58.8. Oh, I don't need a bracket there. that back. There. 58.8 newtons. What else is acting on this guy? Tension upwards. And because these two tensions are the same, I don't need to label them 1 and 2. They're equal, they're opposite. I can use the same labeling for both. This is it for the free body diagram. The single most common mistake I see on problems like this is students get a little overexcited labeling their forces in their free body diagram, and they will toss a normal force on this hanging object here. That's why I've been hounding you guys so much about what a normal force actually means. If you're sitting on a surface, a normal force is acting opposite the surface. This thing's not on a surface. There is no normal force on the hanging object. So if you're going to analyze it like this, what direction are we going to call positive? Just down? Because we've got things acting in different directions here. As soon as you see a pulley, you can't just say down. So then what's that going to look like over here? For this block, which way is positive then? Positive is going to look like this, to the right up here and down over here. When you're labeling positive on this diagram, that's what this thing's going to need to look like. This block has tension acting to the right positively. The pulley changes the direction we call positive, and now down here, down is positive. So again, I'll demonstrate it with picking it up and pulling on the pulley. If I pick this thing up and I lay it out flat, it's going to end up looking like this. The 8 kilogram block is going to be here. This thing was sitting on a flat surface, so really it's just this one that gets picked up, spun over, and slapped down here. So this one's still going to have FG acting down, FN acting up, tension acting to the right within this rope. But now for the 6 kilogram one, tension is going to be acting to the left. And this FG is going to be acting which way on this block? In this diagram. To the right. Good. And we had a value for that, 58.8. So your free body diagram should always be done on the diagram for the actual situation. And then if you want to pick it up and analyze it this way, you're welcome to. Just make sure you're consistent with what you're doing to the directions. These two were sitting on a flat surface. This thing's not impacted by the pulley. This is still up, that's down, that's right. This guy that was up is now left, and this guy that was down is now to the right. The pulley has changed the direction there. So if we said that this way, right and down, or clockwise was positive, that means to the right is what we're going to consider positive in this problem. So now we can go through and we can find the acceleration. F net equals ma. If to the right is positive, start at the right and start labeling your forces. We're going to have this 58.8 is going to be positive because it's acting to the right. That's acting to the left, so it's going to be minus Ft plus Ft. And that's it. These two cancel each other out. These two are also not acting in the direction of motion of the 8 kilogram block. They do not need to be included in the F net equation. This is then just going to equal your combined total mass of the system, 14 times A. So now we can go through and we can solve this. These two are going to cancel. We're going to get 58.8 equals 14A. A is going to equal, I did the math before, 4.2 meters per second squared. to go through and find the tension now in the string, which block do you want to isolate, the 6 kilogram or the 8 kilogram? Why? You sure? Well, now I'm asking the question. Now you're unsure for sure. So this one's going to have Fg minus Ft. If we look at F net equals Ma, how many forces does this one have acting in the direction of motion? So which one's actually simpler? You could use a 6 kilogram block. You're not going to like, it's not like one or the other is better. Both will give you the right answer. But in this case, because there's no friction, this one's way easier. But again, it doesn't matter which one you choose. You want to do the 6? We can do the 6. Do you still want to do the 6? Just do the 8? Or do you want me to do the 6? Do the 8. Okay. So if we look at the 8 kilogram block then, if F net equals Ma, Ft is acting to the right. It's the only thing acting in the direction of motion. So that's going to equal 8 times 4.2 . 8 times 4 is 32. 8 times 0.2 is 1.6. You're going to have a tension force of 33.6 newtons. And again, it doesn't matter which one we would have used. We would have got the same thing if we looked at the 6 kilogram block. I can show you because last semester they did the 6 kilogram block. The math works out, it's the same value. It's slightly more work. You got to keep your negatives straight. But otherwise, it's the same. So this thing's going to move. This acceleration is a positive value, which means what we expected to happen is going to happen. We said to the right and down. Well, if this thing's going to move, that's how it's going to go. So that's the acceleration of the system. Let's look at the same thing again. Look at it two different ways. I've got the same system. There's a friction force of 25 newtons. Now, if you recall, friction force comes from this expression. Force of friction is equal to mu times Fn. In this case, the Fn that we're concerned about is the Fn on the 8 kilogram block. So we've got Fg, we've got Fn. We could calculate these and multiply it by the coefficient of friction. Well, we are told, though, in the question that there is a friction force of 25 newtons acting on the 8 kilogram block. Which way is it going to act? It has to act to the left. Even if we don't know which way the system is, even if we don't know if the system is going to move, if it were to move, it would move this one to the right. It can't, friction isn't going to, the tension isn't going to push this thing to the left. Ropes don't work that way. So we have to draw friction in the direction that it would act if it was present. So this is the way friction is going to act. And they gave us the value. This is equal to 25 newtons. You will not likely be given that value. What you will likely be given is this value here, is mu. They might say something like mu is 0.32. And in fact, a 25 Newton force here, I think, is exactly 0.32. I did my calculation correct. That's going to be 8 times 9.8. Yeah, that's 0.32. A 25 Newton friction force is equivalent to saying the coefficient of friction is 0.32. If I gave you this value, you'd find Fg, you find Fn, you'd calculate. Because I gave it to you, we don't need to do Fg and Fn. We're just going to do the rest of the problem the exact same way we did before. This guy right here is Ft. This guy right here is Ft. Everything else gets labeled the same way we did before. Zoom this in so it's easier to see. This guy's going to be Fg. The value for that is still 58.8. Is this thing going to move? You should be able to do better than might. Is it going to move? You should be able to do better than most likely. You should be able to give me a definitive answer here, Day. Will this system move? Why do you say that? How big is the FG? Sorry, which FG are you talking about? This one or this one? This one, okay. So that's okay. This FG is going to be 8 times 9.8. That is, that's 78.4. So this normal force is 78.4. The friction force is 25. We told that in the problem. So why do you say the system's not going to move? What are the forces in the direction of motion of the system? The tensions. What else? This gravity. And what else? And this friction is going to hold it back. So if we wanted to determine if this thing was going to move, what should we be comparing? These two are going to be equal and opposite, so these two are going to cancel each other out. All we're concerned about is this guy and this guy. Sorry? You're saying it will move? So you went from most likely not moving to definitely moving? They will. They have a value. We're going to go find out what they are. We're going to find out that they're 44 newtons. But they're still equal and opposite. Like they're still acting on. So when we analyze the problem, these two, I said that weird, these two don't actually have any bearing on whether or not the system moves. The only thing that controls movement are these two. If Fg is bigger than the force of friction, it's going to move. If friction, here's an interesting one, what happens if friction is bigger than Fg? Then it won't move. If the friction value you calculate here is larger than Fg, the system will not move acceleration 0. Good. Do you all follow what here it is saying there? He's right. Because I do set up problems like that. I'll give you something like this, and I have students look at this thing like, ah, yes, okay, so my friction force here, that's 70 newtons. And then they'll say, okay, well, this thing is going to accelerate this way. Does friction cause these two things to move that way? Can it? No, friction only opposes motion. Now, if I told you there was an applied force here of 70, would the system move? Yeah, it would. So it has to do with what the nature of this force is. Because it's friction, if this value is bigger than this guy, there will be no motion. And I catch students with that every semester. I'll give them something like this, and they'll be like, ah, yes, the friction is going to cause this thing to fling this way. Kind of. Friction will, and that was part of the applet I wanted you to look at a couple of weeks ago when I was away. Just because it says that if the force of friction here was 70, not 25, friction wouldn't be 70. It would match whatever is pulling against it until you reach that maximum value. And then past that, it would slide. So just so we're really clear on how friction works and what it means, if this was bigger than this, it wouldn't move. But because this is bigger than this, it will slide. We can figure out what that looks like. So, like before, I'm going to call to the right and down positive, because that's the only possible direction this system's going to move in. Friction will not cause this thing to go left and drag this thing up. If it moves, it will only move to the right. So let's take a look at this. I still, this one I'm not going to redraw. This one's going to look like this. Because I called over and down positive, I'm going to start when I'm analyzing my FNet equation, FNet equals MA, I'm going to start down here. I'm going to have my 58.8 working backwards. This FT is up over, so that's going to be minus FT. That is a positive FT. And that's minus a friction force. I know the value for that, so I'm just going to plug that in here. That's 25. And that's going to equal the combined mass of the system, which is 14, times A. This and this cancel. 58.8 minus 25 is 23.8. Nope. 28.8. Nope. It's bigger than that. Come on, read off. Should not need a calculator for this. 33.8. I'll call it because it's the end of the day Monday. I needed a calculator for that. It's embarrassing. 33.8. So we have a net force. So this thing is going to accelerate. What's that rate going to be? Here today, you said earlier it was going to be less than the one that we previously calculated. Divide both sides by 14. 33.8 over 14 is 2.4 meters per second squared. You predicted it would be smaller. It is smaller. Without friction, it was 4.2. With friction, it's still sliding, but at a lesser rate. Sorry? Yes. Yeah, it's sliding. It's still sliding, but it's slower than what it was with frictionless. So now let's find the tension. What do you predict for tension here today? Bigger or smaller? So you're saying it's going to be exactly the same as what we calculated before. Think it's going to be bigger or smaller? Think it's going to decrease. Okay, let's figure it out. Let's analyze. Pick a block. This case, it doesn't matter because both of them have two forces acting in the direction of motion. On the 8 kilogram block, FT is positive. On the 6 kilogram block, FT is negative because it's acting back against what we call positive. So it doesn't matter which one you pick. I like the 8 kilogram block because the FT is positive already. So I'm going to use the 8 kilogram block. For our FNet equation, FNet equals MA, you always need to start there. We're going to have FT positive minus 25 is equal to, we're isolating the 8 kilogram block, so the mass is 8, excuse me. The acceleration of the system we found already is 2.4. So FT is going to equal whatever 8 times 2.4 is, plus 25. That value, I calculated before, is 44.2 newtons. So the tension has increased. We have a larger tension in the rope because friction exists over here. And that's it. Questions, comments, concerns, anything I've done here? Cool, then I want you to play with the rest of the stuff. Everything I did not assign from the previous pages. So 1 and 2 over here. The same kinds of examples we just did. And then 1, 2, 5, 6, 7, and 9. I want you the rest of them on that page. It's 1:50. You've got like half an hour. You have lots of time to get these done. Take a look at those. So these are still tension problems, but the setup for them is different. You have signs hanging outside of buildings held by cables. You've got an elevator at rest. You're going to find the tension there. You've got buckets stacked here. So in a question like this one, you've got multiple ropes. That one's going to have a tension up. And I'm going to call that FT1 because this tension and these tensions are not going to be the same. These are different rooms. So this guy and this guy, we can call them FT2 and FT2, but you have to label them distinctly from this top one. So there are some different kinds of things here, but at the end of the day, it is the same, conceptually, it's the same kind of stuff that we've looked at. Give this stuff a shot. The rest of it is what I want you to look at. On your mark, get set, giver. And tomorrow we're going to go ride the elevator. All of us, we're going to go in the elevator together. It's going to be great. It's true, usually I have to split the class in half, but you guys are half a class, so we're good. It's just going to get cozy when we put all, should be 12 of you? 1, 2, 3, 4. Oh, and Akash is away. Yeah, we're going to go ride the elevator. There's 11 of you and me. And I think, yeah, the maximum weight or mass, I guess, in the elevator, I think it's 2,500 kilograms. So as long as all of us are under 250 kilograms, which we are, we'll be good. It'll just be tight. Okay, get to it.